Hey everybody, we're going to start off with some sample diploma questions. I just got a new microphone finally. They ordered it like 2 months for me to make these videos and I finally got it. So hopefully it works okay. I'm thinking it'll work better because I don't have to record through my phone anymore. Yeah, if there's any audio issues, just let me know and this will make things much simpler for me to make videos, so that's good. Okay, so this first question is one of those tricky questions that deals with, is it classical theory or is it quantum theory? So make sure you give these a go before I go through them. So this first question says, classical wave theory and quantum physics are different predictions make different predictions about the effect of incident electromagnetic radiation on a photoelectric surface. So what we're trying to do is we're trying to match up. We're trying to match up which of these predictions fit with what theory. So number one says low intensity. So this means dim, not very bright light. So low intensity electromagnetic radiation incident on a photoelectric surface for long periods of time will cause photo emission. So to me, this sounds like classical wave theory, where if you shine light on something for a long enough time, that you're going to get photo emission. Let's read the second one. So high intensity electromagnetic radiation will not cause photoelectric emission unless this frequency is greater than the threshold frequency. So the threshold frequency idea is quantum, right? 100% is quantum and doesn't work with that. So the first one's probably going to be classical wave theory. For 3, the energy of the emitted photoelectrons will increase if the intensity of the light is increased. So if we do brighter light, we have more energy. So that is bigger waves. When I was doing that wave demonstration, so bigger waves make them shoot off faster. That's classic wave theory. But what we actually see is if we do brighter light, we get more photoelectrons, but we don't get faster ones. So the energy of the emitted photoelectrons is independent of the intensity of the incident electromagnetic radiation. Yes, intensity will not affect energy. What affects energy is the frequency, the energy of the photons. So 4 would be that one. Those guys are tricky. I hate those questions, but sometimes they pop up, and for sure there's going to be one on your quiz. So make sure you ask me questions if you don't understand anything about that. Okay, so the work function of a surface that has a threshold frequency of that expressed in scientific notation. So this one is super easy. We don't even need that big equation. So to do this one, all we need is that our work function equals h times our threshold frequency. And we have to look at what the units it wants. It wants the answer in joules. So we'd use 6.63 times 10 to the negative 34 joule seconds. And our threshold, I wrote down the wrong formula. It should actually be work function equals hc over lambda, like this, with like a threshold wavelength, because they give us a wavelength. So we go 3 times 10 to the 8 meters per second, and then we put our wavelength down below, which is 7.1 times 10 to the negative 7 meters. So when I plug all of that in, divided by 7.1 times 10 to the negative 7, we end up getting 2.80 times 10 to the negative 19. So our answer would be 2819. I'm just going to toss this pen. She's dead. I got it in the garbage can. Okay, and then this one is a little bit more to it. So a metallic surface has a threshold frequency. So we got our threshold frequency. A photon has an energy, so this is E photon. So the maximum kinetic energy, so not a lot of breaking down of formulas. So this one's not too bad. So this is our EK max equals energy of our photon minus our work function. So the question is looking for the maximum kinetic energy, so we don't need to break this down. And they give us the energy of the photon, so we don't need to break this down. And then the work function, they give us a threshold frequency, so we'd use this and we'd break this down. So it's just going to be the energy of our photon, 2.8 times 10 to the negative 19 joules. And we want to stick in joules, 6.63 times 10 to the negative 34 joule seconds. And our threshold frequency, which is 3.60 times 10 to the 14 hertz. So if we plug all that into our calculator, let me use my on-screen calculator for this one. Just give it a second to open up. You're my first video of the day. Okay. So we're going to go 2.8 times 10 to the negative 19. And we're going to subtract that from 6.63 times 10 to the negative 34 times 3.6 times 10 to the 14. Okay. And we get 4.13 times 10 to the negative 20. So 413 or 4120 would be our answer. So 4120 would be our numeric response answer. Okay. Next one. Which of the following equations represents the relationship among the stopping voltage, the photon frequency, and the threshold frequency for a photoelectric surface? So this is just asking you to take this EK max equals our energy of our photon minus our work function. So we're taking this formula and we're breaking it down. It looks like we want this VQ there, and it looks like they're using HF for this and HFO. And they want to know if you know how to rearrange it properly. Well, if we're trying to solve for V stop, well, we just move the Q underneath there. So HF minus HFO divided by the charge of the electron. So yeah, they're just seeing, do you know how to rearrange an equation? Okay, and then number 26 is our last one. Okay, in a photoelectric effect experiment, electromagnetic radiation that has a wavelength of that is incident on a photocathode, and they give us a work function, and they tell us the photocurrent produced is 2.6 times 10 to the negative 6 amps. The minimum number of photons incident on the photocathode during the 0.5 minutes of continuous operation. Okay, so there's a lot here, and I'm sure when you first did this question, you might have been steered towards using this equation here. But this equation doesn't really tell us anything about the number of photons. Right? So to do this question, what you need to know is you need to know that one photon releases one electron. That's this quantum idea that one photon releases one electron. Okay? So knowing that, what we can do is we can use this current. So remember that current equals charge over time, and we can find out the charge that we get. So it says that it runs for 0.5 minutes, so we'll have to switch that into seconds. So there's 60 seconds in 1 minute, so I guess I could have done that in my head, that 30 seconds. And then our current is 2 times 10 to the negative 6 amps. And when we do that, what we end up getting is 6.5, or 6 times 10 to the negative 5 coulombs. So we did these conversions before. We know that one electron has a charge of 1.6 times 10 to the negative 19 coulombs. So if we take that answer and we divide it by 1.6 times 10 to the negative 19 coulombs, you end up getting that you had 3.75 times 10 to the 14 electrons. So that's how many electrons went past that point. And we know that one photon releases one electron, which means we have to have the same number of photons. So that makes D our correct answer. Okay, so hopefully those went okay. Let me know if you're having trouble with any of these sample diploma questions or any of the workbook questions as well, and we can figure those out. I forgot that this played, it scared me a little bit. So we're learning about the Compton Effect today. Yes, straight out of Compton. So getting down to the hood of this lesson. Okay, anyways, so explain qualitatively and quantitatively the quantum effect as another example of wave-particle duality, apply laws of mechanics and conservation of momentum and energy to the photons. Okay, so we're going to use physics principle number 4 and physics principle number 5 to do these questions. And I'm going to break this into 2 lessons just because it's a longer lesson. And yeah, from your feedback, you said you didn't want longer lessons, so I will break it into 2 for you. So photon momentum. So during the photoelectric effect, EMR crash into plates and eject electrons. So this is very similar to a momentum question where a billiard ball crashes into another billiard ball, right? You take your photon billiard ball, crash it into the electron billiard ball, and then the electron billiard ball shoots out. So if we wanted to calculate 2 billiard ball type questions, we need the law of conservation of momentum. That's what we did in our first unit. But we have a problem when it comes to a photon. Our formula for momentum is P equals mv. But if we try to look up the mass of our light particle, well, light doesn't have any mass. It's a massless photon, so how can we have momentum if we don't have any mass? So E equals mc squared is probably something that you've heard of. Oops. So photon momentum only works for relativistic speeds, so really, really fast speeds. So if we're talking about relativistic speeds, sometimes we say 0.1 c, and that just means that you're moving at 10% of the speed of light, right? So the idea behind E equals mc squared is when a photon is at rest, it has no mass. But a photon can never be at rest, right? So as objects move faster and faster, their energy is converted to mass. So a photon is moving at the speed of light. And if you move closer to the speed of light, you get more and more mass. So a photon has a very distinctive mass. And what we can do is we can rearrange E equals mc squared, and we can see how energy can have momentum, right? So if I write out E equals mc squared, but instead of saying E equals mc squared, I'm going to write it as E equals mcc. We also know that momentum equals mass times velocity. And if we're talking about a photon, well, its speed is always the speed of light, which is c. So mc is equal to momentum. So momentum times our speed of light is equal to our energy, and voila, we have a brand new formula that relates energy and momentum to each other. So this is actually kind of crazy. E equals mc squared is a crazy formula. The equation describes how energy and mass are really flip sides of the same coin. So if mass and energy can actually be converted to each other. So if you see these 2 coins that I have, say you lived in a 2D world where you could just live on this sheet of paper, and every day some 3D god flips a coin and it lands on the sheet of paper, and then you can see this coin here and it either lands heads or it either lands tails, right? But you can only see in 2 dimensions, so you either see the queen head show up or the caribou show up. Well, it's almost like someone grabbing your hand, that 3D god grabbing your hand, taking you to the 3D world and showing Well, these aren't two distinctive things. It isn't a queen day or a caribou day. They're the same coin. They're the same thing. And that's what we saw with E equals mc squared. It's almost like Einstein taking us to the fourth dimension and showing us that energy and mass are actually the same thing, just in different forms, which is crazy. So it's an enormous unification of two very separate concepts in physics. Both matter and energy are the same thing in different forms, and its significance cannot be overstated. It's wild that he was able to unify these two ideas. Light momentum, right? This is the one that I'd rearrange where E equals PC. So if we want to find momentum of light, it's just our energy divided by our speed of light. And this can be combined with Planck's constant, right? So our energy of our photon is equal to HF. So if I take this equation, the momentum of our light, and instead of writing E here, I write HF over C. Well, now we have new equations for our momentum of our light. And we could also say that it's hc over lambda as well for our energy of our photon. So instead of writing energy, I can write hc over lambda, and then just throw that c down below as well, right? Because there's already a c underneath here, so this c and this c are the same, and then the energy is just hc over lambda, and look at that. The c's cancel out, so you get another equation for a momentum of your light. It equals h over lambda. So we have these formulas on our formula sheet. They're all these formulas are found over here. So we have momentum of light equals h over lambda, and we have E equals pc. So the number one mistake that people make with these formulas is this and this and this only work with light. They work with photons. Sometimes people try to use these equations with electrons and they don't work. So never use these with electrons, except for one situation, which we're going to learn later. But for now, don't ever use it with electrons. It doesn't work. So if you want momentum of electron, you use mass times velocity. It does not work with electrons, just photons. So what is the momentum of an X-ray with a frequency of 9.1 times 10 to the 15 hertz? So if I want to do this one, I can use either of those equations. I can use E equals PC, or I can use P equals H over lambda. I'd probably use this one where our energy is just HF equals PC. And then we want to find momentum, so I'd move C underneath here. So the H when dealing with momentum, because when we talk about momentum, it's mass times velocity. So our momentum is in kilograms meters per second, and we still want it to be in kilograms meters per second. So we have to use the joule, the 6.63 times 10 to the negative 34 joule seconds, because if you use the electron volt one, you won't get those units of kilograms meters per second. Okay. And our frequency is 9.1 times 10 to the 15 hertz, all divided by the speed of light. Oops, this is h over lambda, not h over c. So if we plug this in, we get 6.63 times 10 to the negative 34 times 9.1 times 10 to the 15 divided by the speed of light, and you get 2.01 times 10 to the negative 26. And because it's momentum, we get kilograms meters per second, and a photon isn't going to have very much momentum, so getting really, really small numbers is going to be very normal for these. Okay. So let's try a board question. So pause the video and just write it down on a piece of paper and see if you can find the momentum of a photon that has an energy of 4.5 electron volts. Okay, so I'm basically trying to trick you guys, not trick you, but make you make a mistake here so you don't make one in a test. Most people would use E equals PC, but like I said before, our energy has to be in joules or else we don't get those kilograms meters per second. So the first thing you'd have to do is take your 4.5 electron volts and convert your electron volts into joules. So 4.5 times 1.6 times 10 to the negative 19, and we get 7.2 times 10 to the negative 19 joules. Okay, so now all we have to do is we have to take our energy divided by c, so we take our 7.2 divided by the speed of light, and we get 2.4 times 10 to the negative 27 kilograms meters per second. Okay, so if you didn't convert that into joules first, then do it next time. Yeah, don't make that mistake on a quiz. This is as far as I'm going to go today. So you can do some of the homework though. So we'll do all this tomorrow. So you can do photon momentum stuff. And yeah, I think that's it. So you can do this stuff, and then the other stuff will have to wait till tomorrow. Okay. So if you have any questions, shoot me an email, and that is all. Hey everybody, welcome back to part 2 of the Compton Effect. So in part 1, we found that photons, which don't have any mass, can still have momentum, right? And we rearranged some equations, use E equals mc squared to try to figure that out, and we had a couple of new equations. So now what we have is we have someone testing Einstein's theory to see if this is actually correct, if photons can have momentum. So the person who tested that was Arthur Hawley Compton, and he tested the theory of photon momentum, and what he wanted to do was shoot high energy X-rays, so high energy means high frequency, at metal foil. Okay, so shoot light at matter and see what happens. So when Compton observed, what Compton observed was scattering of light waves into two types, one of the same wavelength and one of a longer wavelength. So here's a little picture. So we shot an X-ray, so we shot light at an atom, and after it hit that atom, he got some light to be the exact same wavelength, but then he got some light to be a longer wavelength, and longer wavelength means lower energy. Cool. So that was this experiment. Now we need something to explain it. So this was his way of explaining it. So Compton interpreted these results as meaning the X-rays had momentum very similar to a very small mass particle like an electron. Okay, so we can find the mass, I'm doing air quotes, but you can't see it, find the mass of an X-ray with a frequency of 1.01 times 10 to the 20 hertz. Okay, so we can find that mass. So to do that, we need a couple formulas from our formula sheet. So because an X-ray is light, we can use momentum equals h over lambda, right? And yeah, I guess, or we can use E equals PC and move this down here. This is probably the easier way of doing it. And we know that energy of a photon equals HF. So it equals that. We could also do it here because we could use C equals lambda F, and lambda is equal to C over F. So instead of having lambda here, I can go C over F, and then the F would move up top there, and I get the same thing. So it doesn't matter which one you use. This one's just a little bit easier, I think. I don't know. It doesn't matter. So we end up getting this formula here. HF over C is equal to our momentum. And if we want to relate momentum to a mass, then we just have to go mv, right? But this v here, well, the photon moves at the speed of light. So instead of saying v, I can say c. So we end up getting hf over c equals mc, and then the c would just go down there, which would end up squaring it. Okay, so we want to stick with joules, so 6.63 times 10 to the negative 34 joule seconds. And the frequency they gave us in the question is 1.01 times 10 to the 20 hertz. And then we'd have to divide it by the speed of light squared. And we can find the mass, again, doing air quotes down there. Okay, so we end up getting 6.63 times 10 to the negative 34 times 1.01 times 10 to the 20 divided by the speed of light squared. And we end up getting 7.44 times 10 to the negative 31 kilograms. So what's key to this, let me move this out of the way. What's key to this is its mass times 10 to the 31. Is there anything else that has a mass of times 10 to the negative 31? Well, yes, the electron. So the mass of this X-ray and the mass of this electron, air quotes mass for the X-ray, are very, very similar. And if you want to test momentum, you need two similarly sized objects, right? So if I throw a basketball at a cruise ship, obviously that's not going to make a big difference. But if they have similar mass, if I throw a basketball at a basketball, then yeah, those are going to be very similar. So this was very important in his experiment. So two possible situations can happen when the X-ray strikes a metal foil, right? So it can strike the nucleus, or it can strike the electrons around the atom, right? So the nucleus of the atom is protons and neutrons, and it's extremely heavy, super, super heavy. Protons, neutrons, 2,000 times heavier than electrons, right? Electrons are nice and light. So when the X-ray struck the much more massive atom, it was like a ping pong ball hitting a bowling ball, right? So the atom is a bowling ball. The photon of the X-ray photon is a ping pong ball. Well, it's not going to do anything to the bowling ball, right? With the ping pong ball bouncing off with essentially the same speed and same momentum, and this is seen as X-ray scattering with the same wavelength and energy. So we shoot the X-ray at the much, much more massive atom, and it just bounces off and maintains the same speed, doesn't really change at all. But when the X-ray struck the similarly massed electron, it was like a ping pong ball hitting another ping pong ball. In so doing, oh fancy, the incoming X-ray ping pong ball loses some of its speed as the electron ping pong ball absorbs some of the incoming ping pong ball's momentum, right? So the X-ray hits the electron gains energy. So law of conservation of energy says that the X-ray must lose some of its energy. Same thing with momentum, right? This X-ray has all the momentum to start, so it's going to lose some of the momentum when the electron gains momentum. So the incoming ping pong ball loses speed and momentum, as seen in the X-ray scattering with longer wavelength and lower energy. So that's why they get that longer wavelength coming off. Okay, so when doing Compton scattering questions, an X-ray hitting a electron, what we see both energy and momentum conserved. So when we did momentum in our first unit, we talked about elastic and inelastic collisions. So when we were doing stuff in our first unit, it was like trains hitting cars and all that stuff. And what we found is that momentum was conserved as long as we made it an isolated system. But our kinetic energy was never conserved. So this is different. This is subatomic particles, and when it's subatomic particles, you can have elastic collisions, and these collisions are, for the most part, elastic. So they don't lose any kinetic energy. So Compton made a formula for us, and he combined together physics principle 4 and physics principle 5, and he made this nice fancy formula for when that second situation happens, when that X-ray hits an electron. So this is a formula that he made for us. Change in wavelength equals h over mc minus 1 minus cos theta. So it's a weird formula. delta lambda is our change in wavelength, h is our Planck's constant, m is our mass of our scattering electron, c is speed of light, and cos theta is the angle at which the X-ray scatters. So this is important. A couple mistakes that people make. So you have to use your 6.63 times 10 to the negative 34 joule second Planck's constant, because mass is in kilograms, meters per second. It has to be in joules, so we have to use this one. And the mass is the electron, but the angle is the X-rays, the angle the X-rays are scattered at. Okay, so you can find this one on your formula sheet under quantum mechanics and nuclear physics. Everything in this last couple of units is just on the right side here, so it's right here on your formula sheet. And crazy, we have 1 unit left, but we only have 1 formula left, and we've used all of them on here. I got a mouse pad too, so that hopefully it doesn't jump up like it was doing there before, and it seems to be working pretty well. A little bit nicer writing. Okay, so let's try it out. So a photon of light of wavelength 7.10 times 10 to the negative 11 meters collides with an electron at rest. So the electron's always going to be at rest, which is kind of silly, but yeah. The new photon scatters at an angle of 78 degrees. So this is my 78 degrees here. What is the wavelength of the new photon? Okay, so anytime you are given the angle at which the photon scatters, not the electron, the photon, the X-ray, that is when you want to use this formula. Okay, so we're going to use this formula, and I'm going to show you how it works. So we get delta lambda is equal to h over mc, 1 minus cos theta. So that's our formula that we have there. And really we just need to plug stuff in. This you always get the same value. It's always going to be 6.63 times 10 to the negative 34 joule seconds. Your mass is always going to be the mass of your electron, and c is always going to be the speed of light. So you're always going to get the exact same answer for this first part. The only thing that's going to change is the angle of our photon. Right, so this one was 78 degrees. And don't worry about RCS or anything like that. Just always plug in the angle as is. Always, 100%. I will never make it from the vertical, or I'll never make it weird. Just always put in whatever I give you as the angle. Don't switch it to RCS. Okay. So plug in all this in. Maybe I'll use my on-screen calculator, even though I struggle with it. So I'm going to get 6.63 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 times 3 times 10 to the 8. And I'll just get an answer for that. And then I'll multiply that by 1 minus cos of 78. And I'll double bracket it at the end, and we get 1.92 times 10 to the negative 12, and that would be meters. So a lot of people will stop here and they'll be like, plug this in, I'm a genius, I got the right answer, but this is the wrong answer, because remember that this is equal to our change in wavelength. So if we want to find our wavelength of our new photon, we have to say that change is always equal to our final minus initial, our 2 minus 1 or anything like that, right? So we want to find this final wavelength, which means I have to add on my initial wavelength to that. So I have to add on the 7.10 times 10 to the negative 11 meters. I have to add that on. Remember that the second one should always be longer. So when I add on that 7.1 times 10 to the negative 11. Just making sure that's correct. I end up getting 7.29 times 10 to the negative 11 meters. And that would be my answer, right? My answer would be 7311 on a numeric response. So don't get that wrong because you forgot to change the wavelength. It's actually a really easy question, and it's kind of stupid that they put this in there. But once in a while you get this formula on here, and it's going to be on your quiz, and you just plug in the stuff, and it's really straightforward and easy. Okay. So the less straightforward and easy questions are these types, and this is why I have a whole lesson with this, but there's not very much material. So this is oh, we have a board question after this. Cool. We will do the board question after. So we're going to do this question here. X-rays with a wavelength of 2.035 times 10 to the negative 10 meters are headed due east. X-rays headed due east collide elastically with electrons initially at rest. After the collision, the electrons recoil at a speed of 4.21375 times 10 to the 6 meters per second and an angle of 53.38 degrees. Calculate the momentum and the angle of the X-ray. I don't know why it says meow there. Someone must have put that in there. And the X-ray photons, not meow. Okay, so the reason that you can't use that first formula that I showed you is we don't have the angle of the X-rays. Okay, you need the angle of the X-rays to plug that in because, right, the only thing that you're actually putting in here is the angle of that X-ray. So if you don't have the angle of the X-rays, then you can't use that formula. So what we need to do is we need to use our physics principle number 4, where our sum of all our momentum before equals sum of all our momentum after. That's what we need to do. Okay, and that's what we will do here. Initially the electrons, let's draw a little picture. So we have our X-ray, that's our X-ray photon, and it's traveling at the speed of light and it's got momentum. And then we have our electron here, which is initially at rest. So this is my before. So after, it says that after the collision, the electrons recoil at a speed of, so it gives us the speed and gives us the angle. So our electron fires off at 53.38 degrees. And some fast speed, 4 times 10 to the 6, and I'll use the full number there. So that means that our X-rays must go at some angle downward like that, and we need to find out, well, what's that new wavelength? Since it loses some of its energy, some of its momentum, it's got to be a longer wavelength. Okay, so this is a 2D question, so we need to solve it in the X first. So before, we just have momentum of our photon. Let's call it X-ray. Momentum of our, no, I don't want to have X in there. So momentum of our photon is all we have before. And then after, we have momentum of our photon after, and we have momentum of our electron after. So the key to doing these questions is that if we're talking about light, if we're talking about photon, we're going to use h over lambda. And because it's in the X, we want to go cos of our angle, right? X is always cos. And then after, we have our momentum of our photon after. And then because this is an electron, we want to go mass times velocity, right? And then cos theta. Don't ever break down what you're trying to find until the very end. And I should have actually rearranged this before, but we have to subtract an mv cos theta from both sides. So we get h over lambda cos theta minus mv cos theta equals the momentum of our photon in the X after. Okay, so h over lambda for light, mass times velocity for electrons. So So 6.63 times 10 to the negative 34 joule seconds divided by our initial wavelength, which is 2.035 times 10 to the negative 10 meters. And then our original angle is 0 degrees. It's going straight east. Right? And we're going to subtract our mass of our electron and our velocity of our electron. And then we're going to cos that angle, which is 53.38 degrees. Okay, and that's going to equal our momentum of our photon after in the x. So exactly the same as we did in our first unit, just h over lambda instead of mass times v for everything. Okay, so let's plug this all in. Let's do this calculator. So we can do the same thing for y. So we're going to do all in one. 6.63 times 10 to the negative 34 divided by 2.035 times 10 to the negative 10. I'm going to be very careful today so I don't make a bunch of mistakes for you guys. Okay, I'm going to close that bracket, and then I want to multiply all of that by cos of 0, and then close my bracket. And then I'm going to subtract, just need one bracket, 9.11 times 10 to the negative 31 times 4.21375 times 10 to the 6 times cos of 53.38, and then double bracket to finish. And if I type that all in correctly, cool, that's the momentum of my photon after in the x. So if I want to do y, just like before, all I have to do is switch my coses to sines. So I'll switch this to sine, and I'll switch this to sine. Double check that I'm in degree mode. Yes, I am in degree mode, and then push enter. So this is my momentum in my y. Okay, it's all exactly the same except for we use sine. Okay, so those are my two momentums. So what I can do is, I'm just going to erase this here, is I can draw out my triangle. So in the x, it's positive. So I get 9.68 times 10 to the negative 25. Right? And in the y, it's negative, and it is bigger. Times 10 to the negative 24 is bigger. I'm going to do a longer arrow, and I'm going to do 3.08 times 10 to the negative 24. And I'll use those full answers. So that's where my photon is going. So if I want to find my total momentum, then I just have to take this squared plus this, and I like to get rid of my negative, squared, and then I'll square root it. So Pythagoras, so what I'm doing, so I get 3.23 times 10 to the negative 24 kilograms meters per second. So that's my answer for my momentum. And then my angle, I have to tan -1 of opposite over adjacent. So I'll tan -1 of opposite, which is this one. And I don't like those negatives on there. I never trust them. So I'll take that off. So opposite over adjacent, which is my 9.68. And I get my angle to be 72.6 degrees. Okay, so we've done this already. A little refresher from the beginning of the year, which I think is good when you have a diploma to write, but you don't. But I will have something at the end to help you boost your marks, so you do need to know this stuff at the end of the year. Okay, so that's how we get our answer. But there's another way to get our answer. So I use physics principle number 4 to find this, but I can also use the law of conservation of energy. I can do this exact question. I'm just going to put my answer up here. So 3.23 times 10 to the negative 24 at 72.6 degrees. So that's my answer. So I'm going to do this exact question with physics principle number 5. Someone keeps texting me, sorry about that. So with physics principle number 5, we say that our energy before equals our energy after. So before, we have our photon energy, and then after, we have our photon energy after, and we have our energy of our kinetic energy of our electron after, right? So energy of the photon is just HF. Someone's breaking into my room. And then we have HF after. Hey, actually I'm going to use HC over lambda because we're dealing in wavelengths. And then this is 1/2 mv squared, and that's our electron. Oh, Mr. Pandos just stole a pop from me. What a jerk. I'm recording a video. Get out of here! Sorry, you can't see that. Sorry if that was loud in your headphones. Okay, so we have to rearrange this, which is a little bit of work. So we want to find our wavelength here. So we'll have to subtract a 1/2 mv squared from both sides. So we get h over c minus 1/2 mv squared, and that equals hc over lambda after. This is our wavelength after. So what we could do is we could move this up top, and then we could move this whole thing down below. So we get hc over lambda minus 1/2 mv squared down below. So as long as you move those together, you can move them down below. And let's see what we get. Or I should put the numbers down for your guys' sake. So we get 6.63 times 10 to the negative 34 joule seconds, speed of light, divided by, oh, I ran out of room. Let me start up a little bit higher. 6.63 times 10 to the negative 34 joule seconds, speed of light, divided by 6.63 times 10 to the negative 34 joule seconds, speed of light. They don't cancel out because of order of operations, so don't cancel them out because it's hc divided by, oh, I ran out of room again, but it's that initial 2.035 times 10 to the negative 10. You'll see me type it in my calculator, sorry. I was not good with my spacing. Minus 1/2 mass of the electron, and the speed of the electron sorry, that was super messy, and you probably can't see any of that, and that was a waste of time. But I will type into my calculator. So I'm going to do this bottom first, because this bottom is more complicated. So I'm going to go 6.63 times 10 to the negative 34, that's this h here, times the speed of light. Sure, we get an answer, and then divide it by our initial wavelength, which is 2.035 times 10 to the negative 10. So that's this, and I want to subtract 1/2 times my mass of my electron times the speed of my electron that's this whole bottom thing now. Okay, so you're probably wondering why I'm not using the angle, and it's because we're using energy, and energies are scalars. Energies don't have direction, so you don't need the angle if you're using the law of conservation of energy. So this is the bottom here, so all I have to do is take 6.63 times 10 to the negative 34 times the speed of light, and I need to divide it by my answer that I got, which is the whole bottom there, and I get that as my answer. Oh, and that made me realize that I didn't answer. Oh no, we want to find, so this is the wavelength of our momentum, of our photon, right? So that we found the wavelength. So to find the momentum, we need to go h over lambda. So we need to take 6.63 times 10 to the negative 34 and divide it by that answer. And then we'll have momentum, and hopefully it'll be the same, and I didn't make any mistakes. Yay, 3.23 times 10 to the negative 34. So we got the answer with both techniques, both ways, but the only problem is that the question did ask for the scattered X-ray angle, and we can't find the angle with energy because energy is a scalar quantity. So we could only answer part of the question with this one. So that's why momentum is a little bit better, because momentum allows us to find angles if we need it, and it works in every situation. Energy is just a little bit easier, but it is tricky to rearrange this, so hopefully that went okay. So I have a board question here. I'm exhausted from this already. How long have we been recording? We're at 30 minutes now. So yeah, we'll do the board question. So give this a go and see if you can do it, and I will go through it right. Meow. Maybe I did put that in there in the past. So X-rays with a wavelength of that headed straight east strike a stationary electron. The X-rays scatter at an angle of 45 degrees north of east. So it gives us the X-ray scatter. And it gives us a new wavelength. So that formula wouldn't really be helpful because we already have all that information. We want to find the speed of the electrons, right? So if you were thinking using that other formula, let me just switch this and find my brush. So if you're thinking of using this hc over m or whatever it is, 1 minus cos theta, I forget, I only use this once a year, h over mc. So we have the angle of our X-rays, but we also have this. So that wouldn't give us any information. They give us all the information we have. So we're going to use the law of conservation of energy or momentum. You should get the same answer. I think they're a little bit off if you want to try both. I prefer to use physics principle number 4. I like momentum before equals momentum after. I know it works in 100% of the situation, so if I use that on a test, I'll never get it wrong if I use the law of conservation of momentum. Okay, so initially we have photon momentum of our photon, and then after we have momentum of our photon and momentum of our electron after. And it's in the X because it's a two-dimensional problem. So I'm going to break this down into h over lambda. I need to work my spacing better. So it's h, actually, let's rearrange this first. So we're trying to find this. So we'll subtract momentum of our photon after in the X first. So we have momentum of our photon in the X before, minus momentum of our photon in the X after, and that's going to equal the momentum of our electron in the X after. Okay, so because it's a photon, we use h over lambda. Because it's X, we use cos theta. Because it's a photon again, we use h over lambda. It's the X cos theta. So this is going to be our after wavelength, and we can find the momentum of our electron in the x. So we get 6.63 times 10 to the negative 34 divided by, so this is our initial wavelength, 1.88 times 10 to the negative 11 meters. And it's headed straight east, so 0 degrees, minus 6.63 times 10 to the negative 34 joule seconds, divided by our new wavelength, 1.95 times 10 to the negative 11 meters, a little bit longer, and then cos of, and it says 45 degrees north of east. So 45 degrees north of east is just going to be 45 degrees in RCS. If you're using conservation of momentum, you have to be in RCS. But if you're using that other formula, you should just give the angle that's given. Okay, so now we're ready to plug this in. So I'm going to do it all in one. Okay, so that's my momentum in the x, and then I'll just push second enter and switch all my coses to sines. And that's my momentum of the y, and it goes down, which makes sense because it should. So I need to, so I can draw my triangle. So it's going that way and that way. So I'm going to find this. And remember that we're in momentum still. So if I take this squared plus this squared and get rid of that negative, and I square root my answer. So that's our momentum that we get, but it's asking for the speed, find the speed and its angle. So I'm going to take this, and remember that this is an electron, so we're going to use P equals mv. So if I divide it by the mass of the electron, I can find my speed. So I'm going to divide this by 9.11 times 10 to the negative 31, and I get the speed of my electron. Make sure it's not faster than the speed of light. 1, 2, 3, 4, 5, 6, 7. It is not, so that's good. So 2.9 times 10 to the 7, and then to find our angle, this is our x and this is our y here. So we want to find this angle. So we're going to have to tan negative 1 of our y. Oops. Let's try that again. Tan negative 1 ry. Get rid of that negative. Ah! Tan negative 1 ry. Push clear instead of delete. Divided by our x. Opposite over adjacent. And I get 64.97 degrees south of east. Okay, so that's what you should get for your answer. Hopefully that goes okay. You should have done these already. So you got conservation of energy and momentum, Compton scattering, and then 2D questions. And here's a little bit of unit review if you want to do that. Yeah. So these are just some more questions that you have down there. And as always, if you have any questions, please email me. We can do a Google Meet. We can just answer via email. We can do anything you'd like. So shoot me an email if you have any questions, and I'll be more than happy to answer them. Hey guys, so I'm going to go through these sample diploma questions. Make sure you try them on your own before you watch me do them. Okay, so one example of Compton scattering. So it shows you a 2D Compton scattering, and it gives you the photon momentum to start, and then the scattered photon momentum. Cool. And it gives you the direction of both, so we want to find the magnitude of the momentum of the free electron after it is hit by the incident photon. Cool, so let's do that. So it's a 2D problem, so we're going to use physics principle number 4, where our momentum before equals our momentum after. And so before, it looks like we just have photon momentum. And then after, we have photon momentum, and we have electron momentum after. And we want to find the magnitude of the momentum of the electron. So we'll subtract the momentum of the photon after from both sides. So we get momentum of photon before minus momentum of photon after is going to equal the momentum of our electron after. We have to do this all in the x first, and we have to do it in the y. So this is super easy because they give you the momentum. You don't even have to break that one up. So they say that before it has 1.83 times 10 to the negative 23 Newton seconds of momentum. And to make it in the x, we just cos of 0, and then we subtract the final momentum, which is 1.72 times 10 to the negative 23 Newton seconds, and we go cos of 85, right? So we can plug all that stuff in here. So 1.83 times 10 to the negative 23 cos of 0, and then we subtract 1.72 times 10 to the negative 23 cos of 85, and we get that as our answer for our momentum of our photon in the x, and we switch it to y by just switching our coses to sines. And that's what we get. So we can draw our final triangle. So we get 1.6 times 10 to the negative 23. And then we have 1.71 times 10 to the negative 23. So it just wants to know the magnitude. So all we have to do is Pythagoras this. So this squared plus this squared. And then square root that answer. And we get 2.399, so 2.40 times 10 to the negative 23. So we get D is our answer. Okay. So a Compton experiment, an X-ray photon has a wavelength of that. Is an incident on a free stationary electron. The scattered X-ray photon, which has a wavelength of that, travels back the same way. Find the final magnitude of momentum of the electron. So this is actually a 1D momentum question, right? It's still law of conservation of momentum, so I'll still set it up the same way, where we're using physics principle number 4. Our momentum, sum of our momentum before equals the sum of our momentum after, but it's just in one dimension, so we don't have to worry about positives and negatives. Sorry, we don't have to worry about x's. We do have to worry about positives and negatives. So we have the momentum of our photon before, and then after we have the momentum of our photon after, and the momentum of our electron after, right? Okay, so the tricky part about this is that if we take a look at the picture again, whenever we do a 1D momentum question, we have to assign positives and negatives, right? So this one here, we'll go to the right, has a positive momentum. This one has a positive momentum, but this one has a negative momentum, right? We'd assign those negatives to the velocity before, but this doesn't have a velocity, so we have to make sure that we still assign that negative value to this, right? And that's the number one mistake that people would make. We have to make sure that we make this momentum negative, and we can plug it in like that, or we can make our wavelength negative, whatever we want to do. So we want to find the momentum of the electron. So again, we'd end up with, we'd rearrange it. But if we make that negative already because we were thinking about that, we can actually add the momentum of our electron, or our momentum of our photon after, to equal the momentum of our electron. So we actually end up adding them together. So this breaks down to h over lambda. This is h over lambda after, and that's the momentum of our electron. Okay? So we have to put that negative on there. So 6.63 times 10 to the negative 34 joule seconds divided by our initial wavelength, which is 0.130 times 10 to the negative 9 meters. And then we add on 6.63 times 10 to the negative 34 joule seconds. And we add on our 0.135 times 10 to the negative 9 meters. Okay, so I plug that all in. Or I can use my on-screen calculator. So 6.63 times 10 to the negative 34 divided by 0.13 times 10 to the negative 9. And then we add on right, and we get 1 times 10 to the negative 23, so we end up getting B as the correct answer. Okay. If you got that wrong because of the negative, easy mistake to fix. In Compton scattering, same question. In order to derive this equation here, which of the following physics quantities must be considered? So I talked about how it's a mishmash of both the conservation of energy and momentum. Okay, and then 21, which of the following rows matches the phenomenon as numbered above with the model of the electromagnetic radiation supported by that phenomenon? Okay, so when we talked about diffraction, diffraction is a wave property. Waves diffract, particles do not. Interference is a wave property as well. When we talked about these are in our newest book, Compton scattering and photoelectric effect. They can only be explained using the particle model. So 3 and 4 are particle model, and 1 and 2 are wave model. And expect those types of questions on your quiz. You need to know which ones are wave model, which we use wave model to explain, and which we use particle model to explain. Okay, that is all. Good luck on your quiz tomorrow, and if you have any questions before the quiz, let me know and I can help you out.